What we're going to do in this video is review the product rule that you probably learned a while ago. And from that, we're going to derive the formula for integration by parts, which could really be viewed as the inverse product rule, integration by parts. So let's say that I start with some function that can be expressed as the product f of x. It can be expressed as a product of two other functions, f of x times g of x. Now let's take the derivative of this function. Let's apply the derivative operator right over here. And this, once again, just review of the product rule. It's going to be the derivative of the first function times the second function. So it's going to be f. No, I want to do that blue color. It's going to be f. That's not blue. It's going to be f prime of x times g of x times, that's not the same color, times g of x plus the first function times the derivative of the second, plus the first function, f of x, times the derivative of the second, This is all a review right over here. Derivative of the first times the second function plus the first function times the derivative of the second function. Now, let's take the antiderivative of both sides of this equation. Well, if I take the antiderivative of what I have here on the left, I get f of x times g of x. We won't think about the constant for now. We can ignore that for now. And that's going to be equal to, well, what's the antiderivative of this? Well, this is going to be the antiderivative of f prime of x times g of x dx plus the antiderivative of f of x g prime of x dx. Now, what I want to do is solve. I'm going to solve for this part right over here. And to solve for that, I just have to subtract this business. From both sides. And then I am left with, if I subtract that from both sides, I'm left with f of x times g of x minus this, minus the antiderivative of f prime of x g of x, and let me do that in that pink color, g of x dx is equal to what I wanted to solve for, is equal to the antiderivative of f of x g prime of x dx. And to make it a little bit clearer, let me swap sides here. So let me copy and paste this. So let me copy and then paste it. There you go. And then let me copy and paste the other side. So let me copy and paste it. So I'm just switching the sides just to give it in a form that you might be more used to seeing in a calculus book. So this tells us, this is essentially the formula for integration by parts. I will square it off. You'll often see it squared off in a traditional textbook. So I will do the same. So this right over here tells us that if we have an integral or an antiderivative of the form f of x times the derivative of some other function, we can apply this right over here. And you might say, well, this doesn't seem that useful. First, I have to identify a function that's like this, and then I have an integral in it. But what we'll see in the next video is that this can actually simplify a whole bunch of things that you're trying to take the antiderivative of. What we're going to do in this video is try to evaluate the definite integral from 0 to pi of x cosine of x dx. Like always, pause this video and see if you can evaluate it yourself. Well, when you immediately look at this, it's not obvious how you just straight up take the antiderivative here and then evaluate that at pi and then subtract from that it evaluated at 0. So we're probably going to have to use a slightly more sophisticated technique. And in general, if you see a product of functions right over here, and if one of these functions is fairly straightforward to take the antiderivative of without making it more complicated, like cosine of x, and another of the functions, like x, if you were to take its derivative, it gets simpler. In this case, it would just become 1. It's a pretty good sign that we should be using integration by parts. So let's just remind ourselves about integration by parts. So integration by parts, I'll do it right over here. If I have the integral And I'll just write this as an indefinite integral, but here we want to take the indefinite integral and then evaluate it at pi and evaluate it at 0. So if I have f of x times g prime of x dx, this is going to be equal to, and in other videos we prove this, it really just comes straight out of the product rule that you learned in differential calculus. This is going to be equal to f of x times g of x minus, you then swap these around, minus f prime of x g of x dx. And just to reiterate what I said before, you want to find an f of x that when I take its derivative, it simplifies it. So simplify. And you want to find a g prime of x that when I take its antiderivative, so when I take its antiderivative, it doesn't get more complicated. So not more complicated. Because if the f of x gets simplified when I take its derivative, and the g prime of x does not get more complicated when I take its antiderivative, then this expression will maybe be easier to find the antiderivative of. So let's do that over here. Between x and cosine of x, which one gets more simple when I take its derivative? Well, the derivative of x is just 1. So I'm going to make that my f of x. So I could write that over here. So my f of x, I will say is x, in which case f prime of x is going to be equal to 1. And then what would my g prime of x be? Well, my g prime of x, cosine of x, if I take its antiderivative, it doesn't get more complicated. The antiderivative of cosine of x is sine of x. So let me make that my g prime of x. So g prime of x is equal to cosine of x, in which case g of x, the antiderivative of cosine of x, well, it's just sine of x. Or the other way to think about it, the derivative of sine of x is cosine of x. Now you could think about plus c's and all of that, but remember, this is going to be a definite integral, so all those arbitrary constants are going to get canceled out. So now let's think through this. Let's just apply the integration by parts here. In this particular case, all of this is going to be equal to, so I'm saying that is equal to this. I'm going to skip down here. It's going to be equal to f of x times g of x. So that is f of x is x, g of x is sine of x, f of x times g of x minus the integral of f prime of x. F prime of x is just 1. We could write like that. 1 times g of x. G of x is sine of x. So we could write it like this. But 1 times sine of x, well, we could just rewrite that as sine of x. It'll make it a little bit simpler. Sine of x dx, dx. And then remember, this is a definite integral. So we are going to want to evaluate this whole thing at pi and at 0, and then take the difference between the two. But what is the indefinite integral of sine of x dx? Well, if I were to say the antiderivative of it. We know that the derivative of cosine is negative sine of x. And so in fact, if what we want, we could bring this negative sign into the integral. So we could say plus the integral of negative sine of x. Now this, clearly the antiderivative here is cosine of x. So this thing is going to be cosine of x. And now we just have to evaluate it at the endpoints. So let's first evaluate this whole thing at pi. So this is going to be equal to pi sine of pi plus cosine of pi. And then from that, I'm going to subtract this whole thing evaluated at 0. So let me do 0 in a different color. At 0. So it's going to be 0 times sine of 0 plus cosine of 0. So let's see. Sine of pi is just 0. So this is just going to cancel out. Cosine of pi, that is negative 1. And then this is 0. And then cosine of 0, that is 1. So you have negative 1 minus 1. So this all gets us to negative 2. And we are done. Using integration by parts, we were able to evaluate this definite integral. The goal of this video is to try to figure out the antiderivative of the natural log of x. And it's not completely obvious how to approach this at first. Even if I were to tell you to use integration by parts, you'll say, wait, integration by parts, you're looking for the antiderivative of something that can be expressed as a product of two functions. It looks like I only have one function right over here, the natural log of x. But it might become a little bit more obvious if I were to rewrite this as the integral of the natural log of x times 1 dx. Now you do have the product of two functions. One is a function of x. It's not actually dependent on x. It's always going to be 1, but you could have f of x is equal to 1. And now it might become a little bit more obvious to use integration by parts. Integration by parts tells us that if we have an integral that can be viewed as the product of one function and the derivative of another function, and this is really just the reverse product rule, and we've shown that multiple times already. This is going to be equal to the product of both functions, f of x times g of x minus the antiderivative of, instead of having f and g prime, you're going to have f prime and g. So f prime of x times g of x dx. And we've seen this multiple times. So when you figure out what should be f and what should be g, for f, you want to figure out something that it's easy to take the derivative of, and it simplifies things, possibly, if you're taking the derivative of it. And for g prime of x, you want to find something where it's easy to take the antiderivative of it. So a good candidate for f of x is natural log of x. If you were to take the derivative of it, it's 1 over x. Let me write this down. So let's say that f of x is equal to the natural log of x, then f prime of x is equal to 1 over x. And let's set g prime of x is equal to 1. So g prime of x is equal to 1. That means that g of x could be equal to x. And so let's go back right over here. So this is going to be equal to f of x times g of x. Well, f of x times g of x is x natural log of x. So g of x is x, and f of x is the natural log of x. I just like writing the x in front of the natural log of x to avoid ambiguity. So this is x natural log of x minus the antiderivative of f prime of x, which is 1 over x, times g of x, which is x, dx. Well, what's this going to be equal to? Well, what we have inside the integrand, this is just 1 over x times x, which is just equal to 1. So this simplifies quite nicely. This is going to end up equaling, let me put it right there. This is going to end up equaling, all right, x, natural log of x, minus the antiderivative of just dx, or the antiderivative of 1 dx, or the integral of 1 dx, I should say, or the antiderivative of 1 is just minus x. And this is just an antiderivative of this. If we want to write the entire class of antiderivatives, we just have to add a plus c here. And we are done. We figured out the antiderivative of the natural log of x. And I encourage you to take the derivative of this. For this part, you're going to use the product rule and verify that you do indeed get natural log of x when you take the derivative of this. Let's see if we can take the antiderivative of x squared times e to the x dx. Now, the key is to recognize when you can at least attempt to use integration by parts. And it might be a little bit obvious because this video is about integration by parts. But the one way the clue that integration by parts may be applicable is to say, look, I've got a function that's the product of two other functions, in this case, x squared and e to the x. And integration by parts can be useful as if I can take the derivative of one of them and it becomes simpler. And if I take the antiderivative of the other one, it becomes no more complicated. So in this case, if I were to take the antiderivative of x squared, it does become simpler, and it becomes 2x. And if I take the antiderivative of e to the x, it doesn't become any more complicated. So let's assign f of x to be equal to x squared. And we want that one to be the one where if I take the derivative, it becomes simpler, because I'm going to have to take the derivative of f of x right over here in the integration by parts formula. And let's assign g prime of x. Let's assign g prime of x to be equal to e to the x, because later I'm going to have to take its antiderivative, and the antiderivative of e to the x is still just e to the x. So let me write this down. So we are saying that f of x, I'll do it right over here, f of x is equal to x squared, in which case f prime of x is going to be equal to 2x. And I'm not worrying about the constants right now. We'll just add a constant at the end to make sure that our antiderivative is in the most general form. And then g prime of x is equal to e to the x, which means its antiderivative, g of x, is still equal to e to the x. And now we're ready to apply the right-hand side right over here. So all this thing right over here is going to be equal to f of x, which is x squared. And let me put it right underneath. X squared times g of x, which is e to the x, minus let me do that in that yellow color. I want to make the colors match up. Minus the antiderivative of f prime of x. Well, f prime of x is 2x. 2x times g of x. G of x is e to the x. G of x is e to the x dx. E to the x dx. So you might say, hey, Sal, we're left with another antiderivative, another indefinite integral right over here. How do we solve this one? And as you might guess, the key might be integration by parts again. And we're making progress. This right over here is a simpler expression than this. Notice we were able to reduce the degree of this x squared. It now is just a 2x. So let's actually, and what we can do to simplify this a little bit, since 2 is just a scalar, it's a constant, it's multiplying the function, we can take that out of the integral sign. So let's take it this way. So let me rewrite it this way. We can only do that with a constant that's multiplying the function. So let me put the 2 right out here. And so now what we're concerned about is finding the integral. Let me write it right over here. The integral of x e to the x dx. And now this is another integration by parts problem. And so let's again apply the same principles of integration by parts. When I take its derivative is going to get simpler. Well, x is going to get simpler when I take its derivative. So now for the purposes of integration by parts, let's redefine f of x to be equal to just x. And then we can still have g of x equaling, or g prime of x equaling e to the x. And so in this case, let me write it all down. F of x is equal to x. F prime of x is equal to 1. G prime of x is equal to e to the x. G of x is equal to, just the antiderivative of this, is equal to e to the x. So let's apply integration by parts again. So this is going to be equal to f of x times g of x. Now f of x is x. F of x is x. G of x is e to the x, minus the antiderivative of f prime of x, well, that's just 1, times g of x, e to the x. It's just 1 times e to the x. 1 times e to the x dx. And remember, all I'm doing right now, you might have lost track of things, I'm just focused on this antiderivative. That antiderivative is that antiderivative there. If we can figure out what it is, we can then substitute back into our original expression. Now, you might appreciate integration by parts. What does this right over here simplify to? What is the antiderivative of 1 times e to the x dx? Or what is the antiderivative of 1 times e to the x? Well, it's just the antiderivative of e to the x, which is just e to the x. So this simplifies to x times e to the x times e to the x minus the antiderivative of e to the x, which is just e to the x. So minus e to the x. And then we can take this and substitute it back. This is the antiderivative of this. So we can substitute it back up here to figure out the antiderivative of our original expression. So the antiderivative of our original expression, we're getting really close, is going to be equal to, and I'm going to use different colors so we can keep track of things. It's going to be equal to x squared times e to the x times e to the x, minus 2 times all of this business. So minus 2 times, well, this antiderivative we just figured out is this, minus 2 times x e to the x minus e to the x. And if we want, now is a good time to put our plus c. And of course, we can simplify this. This is equal to x squared. I like to keep the same colors. This is equal to x squared e to the x. Distribute the negative 2. You get minus 2x e to the x plus 2 e to the x. And then finally, plus c. And we're done. We figured out the antiderivative of what looked like a kind of hairy-looking expression using integration by parts twice. Let's see if we can use integration by parts to find the antiderivative of e to the x cosine of x dx. And whenever we talk about integration by parts, we always say, well, which of these functions, we're taking a product of two of these, which of these functions, e to the x or cosine of x, that if I were to take its derivative, becomes simpler? And in this case, neither of them become simpler, and neither of them become dramatically more complicated when I take their antiderivative. So here it's kind of a toss-up which one I assign to f of x and which one I assign to g prime of x. And actually, you can solve this problem either way. So let's just assign this one. Let's assign f of x equaling e to the x. And let's assign g prime of x is equaling cosine of x. So let me write it down. We are saying f of x is equal to e to the x, or f prime of x is equal to e to the x. Derivative of e to the x is just e to the x. And we can say that we're making the assignment, g prime of x is equal to cosine of x. And the antiderivative of that, g of x, is also, or the antiderivative of cosine of x is just going to be equal to sine of x. So now let's apply integration by parts. So this thing is going to be equal to f of x times g of x, which is equal to e to the x times sine of x minus the antiderivative of f prime of x. F prime of x is e to the x times g of x, which is once again sine of x. Sine of x dx. dx. Now, it doesn't look like we've made a lot of progress. Now we have an indefinite integral that involves a sine of x. So let's see if we can solve let's see if we can solve this one separately. So let's say if we were trying to find the antiderivative of e to the x sine of x dx. How could we do that? Well, similarly, we can set f of x is equal to e to the x. So now we're reassigning, although we're happy to make the exact same reassignment. So we're saying f of x is equal to e to the x. F prime of x is equal to just the derivative of that, which is still e to the x. And then we could say g of x, in this case, is equal to sine of x. We'll put these assignments in the back of our brain for now. And then, or let me make this clear, g prime of x. Whoops, there you go. So we have g prime of x. G prime of x is equal to sine of x, which means that its antiderivative is negative cosine of x. Derivative of cosine is negative sine. Derivative of negative cosine is positive sine. So once again, let's apply integration by parts. So we have f of x times g of x. F of x times g of x is negative, I'll put the negative out front. It's negative e to the x times cosine of x minus the antiderivative of f prime of x g of x. F prime of x is e to the x, and then g of x is negative cosine of x. So I'll put the cosine of x right over here, and then the negative, we can take it out of the integral sign, and so we're subtracting a negative. That becomes a positive. And of course, we have our dx right over there. And you might say, hey, Sal, we're not making any progress. This thing right over here, we now expressed in terms of an integral that was our original integral. We've come back full circle. But let's try to do something interesting. Let's substitute back this. Or let me write it this way. Let's substitute back this thing up here, or actually, let me write it a different way. Let's substitute this for this in our original equation, And let's see if we got anything interesting. So what we'll get is our original integral on the left-hand side here, the indefinite integral, or the antiderivative of e to the x cosine of x dx, is equal to e to the x sine of x, e to the x sine of x, minus all of this business. So let's just subtract all of this business. We're subtracting all of this. So if you subtract negative e to the x cosine of x, it's going to be positive. It's going to be positive e to the x cosine of x, e to the x cosine of x. And then remember, we're subtracting all of this. So then we're going to subtract. So then we have minus the antiderivative of e to the x cosine of x dx. Now this is interesting. Just remember, all we did is we took this part right over here. We used integration by parts to figure out that it's the same thing as this. So we substituted this back in. When you subtracted this from this, we got this business right over here. Now what's interesting here is if we have essentially an equation where we have our expression, our original expression twice. We can even assign this to a variable and essentially solve for that variable. So why don't we just add this thing to both sides of the equation? Let me make it clear. Let's just add the integral of e to the x cosine of x dx to both sides. E to the x cosine of x dx. And what do you get? Well, on the left-hand side, you have 2 times our original integral, e to the x cosine of x dx, is equal to all of this business, is equal to this. I'll copy and paste it. So copy and paste. It's equal to all of that. And then this part right over here, cancels out. And now we can solve for our original expression, the antiderivative of e to the x cosine of x dx. We just have to divide both sides of this, essentially an equation, by 2. So if you divide the left-hand side by 2, you're left with our original expression, the antiderivative of e to the x cosine of x dx. And on the right-hand side, you have what it must be equal to. E to the x sine of x plus e to the x cosine of x over 2. And now we want to be careful because this is an antiderivative of our original expression, but it's not the only one. We always have to remember, even though we've worked hard and we've used integration by parts twice and we've had to back substitute in, we have to remember we should still have a constant here. So if you take the derivative of this business, regardless of what the constant is, you will get e to the x cosine of x. And it's actually a pretty neat looking expression.